And now the application. Take a look here. What do we have? We have a parcel of air, a bubble of air in the middle. That's 90 degrees, the red numbers, okay? Then the air that surrounds it is 89 degrees. This is at sea level, okay? So we have a parcel of air at 90 degrees at sea level, and the surrounding atmosphere is 89 degrees. For whatever reason, and we don't know whatever the reason is, but for whatever reason, the reason is really because we need a math problem, of course, what's going to happen is that parcel of air is going to rise. And here is what it's going to do. The parcel of air is going to rise up to 2,000 feet, then it's going to continue to rise up to 4,000 feet. And now we know at 2,000 feet, the parcel of air is going to reach its condensation level, which means now it's 100% relative humidity. Therefore, from 2,000 feet up to 4,000 feet, there's going to be a cloud forming. Okay? Now what we want to do is we want to put some math on this. And once we put all the math on this problem, then we will determine whether this parcel of air is stable or unstable and what it's likely to do because of those things. So first, the air is going to rise from 0 up to 2,000 feet. Is there a cloud forming from 0 to 2,000 feet? The answer is no. So which rate would we use? Think about it. Air is moving vertically, no cloud. That means less than 100% relative humidity. Then the air is going to rise from 2,000 to 4,000 feet. Is there a cloud forming from 2,000 to 4,000 feet? There is. That means 100% relative humidity. Do you remember which rates we're going to use? Well, from 0 to 2,000 feet, we will apply the DAR, the dry adiabatic rate, 5.5 degrees Fahrenheit per 1,000 feet. And from 2,000 to 4,000 feet, we will apply the WAR, 3.3 degrees Fahrenheit per 1,000 feet. Now look over on the left side. I'm telling you for the sake of this problem that the environmental lapse rate on this particular day is 4.5 degrees Fahrenheit per 1,000 feet. I just made this up so we have a problem, okay? I could have said 2.5. I could have said 1. I could have said 8. But I decided to go with 4.5 just so we have a nice little math problem here, all right? That means that the air that is not moving vertically is changing temperature at 4.5 degrees Fahrenheit per 1,000 feet, all right? Good. Let's begin to actually do the math. So, the parcel of air rises from 0 up to 2,000 feet, and we're in agreement that we use the DAR, 5.5 degrees Fahrenheit per 1,000 feet, to calculate the temperature change. So we take 5.5 times 2, representing those 2,000 feet. That would be 11. 11 degrees hotter or colder up there? Colder. Therefore, we take 90, which was the original given at sea level, minus 11 is 79. Now we know that the air temperature in this rising parcel of air at 2,000 feet is 79 degrees. Good. Then the air is going to rise from 2,000 up to 4,000 feet. And we are in agreement. From 2,000 to 4,000, there's a cloud, 100% relative humidity, WAR, 3.3 degrees Fahrenheit per 1,000 feet. And the difference between 2,000 and 4,000 is 2,000. So we take 3.3, the WAR, times 2 for 2,000 is 6.6. Then we take 79, the temperature at 2,000 feet, minus 6.6 is 72.4. This means the temperature of that rising parcel of air at 4,000 feet is 72.4 degrees. All right, we have some math on it now. Now we're going to do this. Find out what the temperature is of the air that surrounds that rising bubble. And we're going to use the ELR to do that, the environmental lapse rate. So again, we have to go up from sea level 0 up to 2,000 feet. We're going to take the environmental lapse rate, something, as I said before, I just made up so we have a problem, so we can determine what the temperature is of the surrounding air, just like I made up the 90 degrees, so I'm making this up too. But the numbers are all fine. This is the problem, so you understand the process that's happening here. We take 4.5, which is the environmental lapse rate, times 2 for 2,000 feet, that's 9. Then we're going to take what? Do you know what happens next? 89 minus 9 is 80, which means that the air temperature at 2,000 feet is 80 degrees. We can see the temperature inside the parcel is 79, but the surrounding air is 80. Now, the air at 4,000 feet is going to be determined like this. We take 4.5 again, which is the environmental lapse rate, times 2 for 2,000, between 2,000 and 4,000 feet. That would be a 2,000 foot difference. That's 9 again. What do? Add or subtract? Subtract. So we take 80, which is the temperature at 2,000 feet, minus 9 is 71. So now we know the air temperature at 4,000 feet is 71 degrees. Okay? Now we have our numbers. So take a look at this, and now you ask yourself this. At 2,000 feet, is the parcel of air warmer or colder than the surrounding atmosphere? The parcel is in red, by the way. The answer is colder. If the parcel is colder than the surrounding air, we would classify it as stable. Good. Now, why doesn't the air subside? Well, we don't know exactly why, but I will tell you something. Cold air can rise. Here's how. Down the street from my house, there are a bunch of kids who ride skateboards. And they built a ramp. And every once in a while, they drag their ramp out into the street. When they do that, they ride their skateboards along, they're kicking on their skateboards, and then they hit the ramp. When they hit the ramp, their volition causes them to rise along the side of the ramp. They don't need to keep kicking, their volition causes them to go up. If you have very cold air that's moving rapidly towards a mountain range, and it hits the mountain range, it's not going to go through the mountain range, and it's probably not going to stop moving. So what it does is its volition causes it to rise. So there are circumstances where cold air can rise. Now let's look at 4,000 feet. At 4,000 feet, the temperature of the parcel is 72.4 degrees, and the temperature of the surrounding air is 71. So, is the parcel warmer or colder than the surrounding atmosphere? Answer is warmer. And if the parcel is warmer, we would classify it as stable or unstable. Unstable. This is how you make violent weather. When you have unstable air in a cloud and that air keeps rising. I'll tell you, if the parcel was 72 and the surrounding air was 50, that would be highly unstable. Then the air would be moving up very rapidly. But this is how you make violent weather. Thunder, lightning, or lightning and thunder, hail, maybe tornadoes. This is how it's formed. Okay? And if you look at that cloud, a cloud we've seen before, that's what's going on. That cumulonimbus cloud is formed from very unstable air. And what's happening is the air inside that cloud is significantly warmer than the air around it, than all the blue sky. And that's what's caused that cloud to rise like that.